Hello, have you ever wondered how a clean, smooth guitar tone transforms into a heavy, distorted rock sound? What if I told you that the secret lies in math? Yes, non-linear functions shape your favorite distortion effects. In this video, we will break it all down. First, the theory behind non-linear functions and how they generate harmonics. Then we will jump into Python to code distortion effects and hear the magic ourselves. By the end of this video, you will not only understand distortion, but you'll be able to create it yourself. Before we move on, let's hear to a guitar clip which compares the original clean guitar with the distortion effect. So this is a clean guitar. Interesting, isn't it? So let's first understand what are linear and non-linear functions. A linear function follows the rule fx is equal to ax plus b, which is nothing but an equation of line, where a and b are constants. Specifically, a signifies the slope and b signifies the intercept. It's just a simple straight line with no curves in it. A pure sine signal or pure sinusoid wave remains a sine wave when processed through a linear system. It does not generate any new frequencies or harmonics. For example, the volume control on your amplifier. It just amplifies the sound, but it doesn't generate any frequency of its own. In contrast, nonlinear functions are the functions which are not of the form that of line. These functions, when plotted, they have curves, they have bends, and they have twists. There are many such examples like quadratic functions, cubic functions or higher order polynomials, exponentials and logarithms, trigonometric and inverse trigonometric functions, piecewise functions, absolute value functions, especially used in rectification, full wave rectifier and half wave rectifier. Then we have power and root functions and rational functions. So these are various such functions, nonlinear functions as plotted, so that you can see that they indeed are having bends and curves. On the extreme left is the linear function, which is nothing but a straight line, signified by 2x plus 3. So such a function doesn't generate any harmonic. Whatever is the input frequency, it outputs the same frequency. Then the second function is a quadratic function, and as you can see, it has one bend in it, and we'll study more about it in the subsequent slide. Then the third function is this cubic function, where we have this cubic term in the function. And an interesting point in all these polynomials is that the order of the equation decides how many number of bends and twists are going to be there in the curve. For example, a quadratic equation has a power of 2, so it will have one bend in the wave. A cubic equation has got a power of 3, so it can have two bends. This is the first, and this is the second. And the higher order polynomials have can twist and turn more. Then we have exponential function, when negative values are all 0, and then positive values, they shoot up. We have a tanh function, which almost looks like a sinusoid, a sigmoid. We then have arctan function, which is almost similar to tanh functions, but have different spectral properties. And we then have a logarithmic function, which looks like this. So what happens when we pass a sinusoid through a linear and a nonlinear system? So as I mentioned earlier, in a linear system, the signal just passes through. Either it gets attenuated or it gets amplified. Its original frequency remains the same, which is shown by the spectrum plot. However, when we pass the signal through a nonlinear system, its time domain waveform changes. In this case, you can see here that it is clipping at the peaks and troughs. And because of these clippings, harmonics get generated. These harmonics are reflected in the spectrum plot of this particular system. So you see there are 3 harmonics in this particular case. A little bit of maths here. So if we talk about a squaring circuit, essentially I'm talking about this quadratic equation. So if we square a signal, there's a trigonometric identity, sine squared theta is equal to 1 minus cos 2 theta divided by 2. So here you can clearly see that the frequency has doubled up. So this half is the DC component and this is the second harmonic. Similar thing happens when we cube sinusoid. So sine cube theta has got a third harmonic in its term, in its expression. What happens if we take an absolute value of sine theta? This is again a nonlinear function, also called as rectification function. And here again, it generates multiple harmonics based on this value of k. What if we raise the power of sinusoid to a higher power? So sine raised to the power n theta. Now this is a very interesting function. It will generate as many harmonics as this n is. For example, if n is 4, it will go up to the 4th harmonic here. And lastly, if we pass a sine signal through an exponential transformation, then this is how it looks like. And then we can expand this exponential in a power series, which is also known as Taylor series. And as you can see, this Taylor series is nothing but a power function. It's a summation of power functions of various sine terms, and hence it will generate multiple harmonics. So now what we specifically want to do is we want to look at these 8 different nonlinear functions, starting from tanh, cubic non-linearity, arctan distortion, exponential saturation, polynomial distortion, asymmetric soft clipping, sigmoid distortion, and hard clipping, and see how they impact the sound. So here is the plan. We are going to first simulate all these 8 nonlinear functions. Then we are going to pass a 440 Hz sine signal and see how it is impacting the sine signal. And then we are going to play a clean G chord on a guitar and hear the distortion effect once they are modified by these nonlinear transformations. So over to code.